Okay, Mr. Jones here, and I want to go over the Chapter 12 first year review worksheet. I have just made a video already, but I didn't share my screen, so that means that you wouldn't see any of my work. You can see I did all the work in the whiteboard, and it is here, and so on. So we'll just keep this and reuse it. And I'll go through some of the bits here that make things interesting. I also need my special little writing pad that I put away. This one's just not meant to be.
That's how I feel right now.
Yeah. Okay. So here we go. Got my special pen. 1, 2, and 3 are very similar in that you're given some information. You have to organize what happens to the chemicals in the reaction and then plug those values into the K expression. So if we look at this first one, let me find I'm going to use some different colors today. Let's use this annoying orange, and let's use, I guess that gray. Let's do the dark gray. And let's use, it looks like it's like a bronze color. Okay, we'll start with that one. I like that one. When you do your ICE chart, remember that I stands for initial, C stands for change, E is equilibrium. Now the initial values are just arbitrary. They're made up by the author. In this case, in number 1, they say the initial H2 is 0.4 and the initial N2 is 0.5. Now this has nothing to do with the reaction. It is not based on the stoichiometry. The reaction hasn't happened yet. This is before the reaction. So don't even look at the coefficients at this point. It doesn't mention any initial product, so I like to put a dash just to emphasize it doesn't even exist yet. After this, they have to give you one other piece of information. And then this particular problem, the piece of information they gave must be something about the ammonia. I need to get my worksheet out because I put it away thinking I was done. Here it is. They said at equilibrium, the ammonia is 0.05. So that gave me this. And then what you do is once you know how that changes, it goes from nothing here to 0.05. The change is 0.05 right there. And now that we know how this chemical changes, once you know how one chemical changes, you can figure out how the others change by using the stoichiometry. Notice I have a negative for my reactants and a positive for my product. That's because I was starting with only reactants, so they must go down and the products must go up. Now that won't always be the case, but it will be on this worksheet to get us started. Now, if I know that this is 0.05, the ammonia, now I look at the stoichiometry up here, and in the stoichiometry, I have 2 to 1 to 3. Well, 2 to 1, that means whatever the ammonia does, the nitrogen must do half that. So 0.05 and half is 0.025. And then whatever the nitrogen does, the hydrogen must do 3 times that. So 3 times 0.025, 0.075. The change row will always match the stoichiometry. So I need to emphasize this. This really is the magic of the ICE chart, is that this row must and always will match the balanced reaction. That's why this chart is useful. Once you know that, you just add all your columns, which gives you your equilibrium values. We already knew that one. Write out your K expression here. Remember, it's always products over reactants, and the coefficients become exponents, and you end up multiplying all your products and multiplying all your reactants. Don't put pluses in there. That's a common mistake. So there's my expression. I plug in my values here from the equilibrium row of the ice chart, solve for the answer 0.153. Right there. Number 2 is similar, except, not even bother showing 3 yet. Let's focus on 2. In this one, the first chemical is a solid. So notice I have it in my ice chart, but they never talked about the solid because solids aren't put in the expression. So I just put a squiggly line just to say, it's present, it's part of the reaction, but not important to what we're doing right now. Notice in my expression over here, the S is not there because it's a solid. Also, they gave us this to start with, no product, so dash again. And this time they said something different. In number 2, they said that the oxygen is 40% dissociated or 40% reacted. So I took 40% of the starting amount. That gave me 0.060, which I put here. And again, once I know how one chemical changes, I can figure out the others. I don't care about the sulfur, but I had to do a 3:2 ratio, and that gave me the 0.040. Got my equilibrium amounts, plugged those into the expression, and got an answer of 2.2 for the final answer here. I mentioned some things about the arrows down here. When you're doing your arrows, you can do a double-sided arrow. You can do 2 arrows. You can do 2 arrows like I do, where you don't quite finish them, but everyone understands it. What you don't want to do is a equal sign. An equal sign in the middle of the reaction, that's like a mathematical thing, and it's saying that it would almost be misinterpreted as saying that the amount of the chemicals are equal, and that is not the case. It's possible, but it's unlikely. In equilibrium, it's the rate of the forward and the rate of the reverse reactions that are equal, not the amounts. All right, number 3, similar, except, what did they tell us this time? They said the hydrogen decreased by 0.025. So here are my starting amounts, here, nothing here. This changed, it went down by 0.025. And the balanced reaction is 1 hydrogen to 1 iodine, so iodine's change is the same. And then 2 HI, so it's double. Add your columns to get your equilibrium amounts. In my first version of the video, I talked about how if you ever get a negative value for the equilibrium, that means something's wrong. The lowest possible value is 0. You can't get a negative amount. You can get a negative change, but not a negative amount. After that, things are pretty straightforward, and you get an answer of 2.37. After this, we go into some shifting problems. And the basic idea here is that if the reaction's at equilibrium, the forward and reverse rates are equal. If you do something, typically referred to as a stress, if you stress the system, it will do what it can to undo the stress and get back to equilibrium. So in the case of number 4, A, if we remove NOCl, it's going to do what it can to make more. So it's going to shift to the left, meaning it's going to go faster to the left right now. Now what will happen is it will slow down to the left, and it will speed up to the right over time until they become equal again. So you can think of it like this. So for 4A, when 4A first happens, when we first remove some NOCl, our reaction will look like this, where we have a lot to the left and then the same that we already had to the right. But over time, it will then switch to, it's still going fast to the left, but not as fast, and it's going faster to the right. And this pattern will continue until they end up back at equilibrium. So this is just at this moment. B, if you add a chemical, it tries to get rid of it. So in this case, since we added a product, it shifts to the left. Pressure, you look at just gases. So in this particular case, there are, I'm looking at 4C now, there are 2 moles on the left of gas, and there are 3 moles on the right. And when you increase pressure, it speeds up both reactions, but it speeds up the side with more moles of gas the most. So in this case, it shifts to the left. D, temperature, you have to look at the delta H. This one has a delta H that is positive, so it's endothermic. So if you decrease temperature, you're hurting the forward reaction, so it goes to the left. And E, volume, pretty much, there's a few different technical issues that come up with volume, but for the most part, volume itself doesn't do anything to the equilibrium or the shifting. It causes a change in pressure, which then does change it. So if you increase the volume, you lower the pressure, and in this case, that shifts to the right. 5, there's not a whole lot to say except for C and E. C is no change because the moles of gas are equal. So in C, if you increase the pressure, you speed up both sides, but you speed them up equally, and so nothing happens to the amounts of the chemicals or the constant value. You just speed them both up equally, and E is also no change. 6, if you add a solid to a saturated solution. Now, when you think of a saturated solution, I think it's best to think of my picture here. So imagine you've got some solid chemical in addition to what you have already dissolved. So this is, let me undo that. That made it worse. Let's keep it the way it was. So let's say you've dissolved as much stuff as you can in water, and you added extra. And that's my pile down here, is just extra stuff that's sitting on the bottom. So we have solid at the bottom of the beaker, and then of course aqueous throughout the solution. This is equilibrium because the solid will continue to dissolve, but at the same rate, what's dissolved will continue to solidify. So the question is saying, let's add some more solid. Well, that's not going to do anything. It's just going to fall to the bottom. It's going to add in, and that'll be about it. 7 is more of the shifting. It's often referred to as Le Chatelier's principle. 8, what is equal in equilibrium? Well, it's the rates of the forward and reverse reactions, not the amounts. 9, how does the catalyst affect equilibrium? It doesn't affect the K value. There's no change in the value of K. That's a U. Looks like it said valve. If we take a look at this diagram that we talked about recently with rates, if our reactants are here and our products are here, our normal reaction has the higher curve, and then the blue curve is the catalyzed reaction. If the reaction's already at equilibrium and then you add a catalyst, you speed up both directions and you don't change equilibrium necessarily. You just get there quicker if you're not already there. So in terms of K, no change. But if you're not at equilibrium yet, you'll probably get there faster. 10, K values are dependent upon temperature. In other words, if you change temperature, you actually change the value of the K. Whereas these other changes we're talking about, like adding a chemical, removing a chemical, changing the pressure, those don't change the value of K. They just cause a shift in the amounts. 11, if we balance using different numbers, then yes, that will change the value of K, and we will deal with that in a future lesson and how to sort that out. 12, we do not put solids into our Ks. because they're considered to be pure. We only put aqueous and gas. Number 12 really isn't that tough. It's more of just a long problem. I think we've done problems that are much more challenging than this, but let's just go through it quickly. In A1, you take the grams, divide by molar mass to get moles, divide by volume in liters to get molarity, which is the answer. A2 is PV equals nRT, solving for P, plug the values in. Now, what I would really like the problem to have done, and I should make a note to rewrite it, is it would have been smart to make A2 relevant in the rest of the problem when we get to B, but it isn't. A2 is just a random question. I would rather it had had something to do with the ice chart later on, but I'll have to change it. Moving to B, B is a lot like problems 1, 2, and 3. You do an ice chart, plug in the values, which we knew this one from up here. So that value got put in there. So we did use a value from A1, but we don't use the value from A2. And go through the steps, and you get the final answer that is. And then at the end, I just mentioned there are a variety of different K values. So Kc, concentration, Kp, pressure, which you're only looking at gases in this case. We're going to focus on these two right now, but we will in time deal with, the next chapter will be KSP for saturated solutions. When we start for second semester, we will have Ka and Kb and Kw for acids, bases, and water. And then we will spend just a little bit of time with something called Kf, which has to do with the formation of a complex ion that you don't know much about yet. We'll be introducing that in the next chapter, not the current chapter on equilibrium. And that should do it. And hopefully this one recorded correctly.